certain individuals. There are people out there who don't believe it and they're actively hostile. And that's their problem. I feel really bad for them. If they can't do it, it's okay. You just don't have to make up fancy stories about why you can. Just admit you're dumb and let's get on with it. Anyway. Theia hits the Earth. There's a thing called the Roche limit. Yep, we've got about 4 minutes, so there's light at the end of the tunnel, ladies and gentlemen. You're doing really well. Thank you for holding up. I know I've been going all over the place. I knew that was going to happen. I think next week I'll be on a better track because now we're going to be able to start following life the way I planned to. So tonight we're dealing with the Hadean. The next session we're going to be looking at the earliest times of life on Earth. What conditions were like, what kind of life might have been there. Then we get down to where we really start to know a lot of stuff. the Diacaran, and then of course the Cambrian, the Great Explosion. You guys are going to love it when we get down here because this is the dinosaur area, right there. But we're mammals, and we're going to look at other things too. And there were some really cool things happened right up here. This is the fish episode when the fishopods appear. I don't know why, I just love that stuff. So there's some really good eras. So we're going to look at the Cambrian. That's going to be exciting because that's those really weird things like Anomalocaris and stuff like that. And then we'll look at how plants evolved, mosses and then plants, fungi, and then how things came out onto the land and vertebrates came out onto the land, the evolution of insects and other arthropods. That all starts up here. All the blueprints for what's going to happen for the rest of evolution are all basically set right up here in the Cambrian from 538 to 485 million years ago. So tonight we're just doing the background here. We're finishing off on the background, but that's the overall background. So in the Roche limit, all that is, it says if you get too close to a planet, the planet will suck you in and destroy you. If you're too far out, you won't get collected at all. You'll just keep going. This was figured out by number 14. Watch this. I feel I'm pretty good here. Isaac Newton. He was the guy. He came up with a thought experiment called Newton's cannon. And in it, he figured out how fast you'd have to be going to escape the Earth's velocity. He really did this. And I think it's 11 point something seconds, kilometers per second. 11 point something kilometers per second. That's how fast you have to be going not to get captured by the Earth's gravity. So you don't get into the Roche limit. But what happened to the moon, I have to go back to the moon now. Not that I'm keeping track of time, not that I'm aware of the fact that we've got 2 minutes left.
It's okay.
But when Theia hit and all that debris was going around in the moon, that was within the Roche limit. And that's why Saturn has got both rings and moons right now. The latest count, there were 293 moons in the solar system. That was as of February 2025. So I don't know how many there are now, but they're finding more all the time. So our moon formed from that collision. Now back to the two-sidedness, and then I'll finish. Two-sidedness, there we go. So they're really different, right? That side is light, that side is 31% dark. This side is covered with craters. This side, oh wait a minute, this isn't a pointer. This is. That side, as you can see, is covered with craters, but not so much where it's dark. See that? Okay, that dark stuff is different than the light stuff. Here's the deal. On the far side of the moon, the crust is 20 to 50 kilometers thicker than on this side, than on our side, the side we can see. Okay? Made out of totally different stuff. This side, this dark stuff there, that's basalt. That's the stuff that forms those cool six-sided columns that you see. You know why it does that? Because that's the most efficient way to get rid of heat. So when basalt's cooling, it forms a hexagon because hexagons get rid of heat faster than anything else. Isn't it? Stuff like that is freaking interesting. Anyway, that's basalt. This over here is an orthosite. Let's see, calcium, aluminum. Yeah, that's an orthosite. It's a mixture. You don't have to know anything about rocks, but this is a crash course for you on rocks. That stuff is light. It's got here, let me see the periodic table for a second.
Which one, full?
Yeah. This stuff, an orthosite, is made out of light stuff. remembering, I've got this. That's stuff like this. So this is the light stuff in the periodic table. This is more light stuff here. And all the rocks, well, okay, just about everything in the universe is made out of this. Okay. Hydrogen, helium, oxygen, nitrogen, phosphorus, silicon, aluminum, and a few things over here. They make up almost everything on the face of the earth. We are made up 95% of carbon, hydrogen, oxygen. That's just about it right there. Throw in a bit of nitrogen, phosphorus, a wee bit of sulfur. That's us. That's over 95% of us is those 5 elements. And those elements are some of the most common ones in the universe. And that's why, probably, we're made of them. But anyway, on the far side of the moon, the near side is mostly basalt, the far side is mostly anorthosite. That's the one with the calcium and aluminum. When you're thinking about rocks, all you really have to know is that there's 2 types of rocks. One, exemplified by basalt, and I won't even give you the name for it, has a lot of metal in it, and it's dark, and it gets runny when it gets wet. The other kind, which is made out of the lighter elements I was just showing you, like aluminum and silicon and calcium, that's the other kind of rock. It's rock like granite. So when you see a dense, dark rock with almost no crystals in it, just really dense, looks like it's all made of one stuff, that's because it cooled under the ground and it's made of denser stuff, whereas if it's a lighter rock like granite, then it cooled above the ground, got big crystals in it, and it's made out of different stuff and looks different. That's your 2 basic kind of rocks. Granite is felsic, basalt is mafic. I told you I wouldn't say that, so I broke my word. And so, finally then, to finish, there's the 2 sides of the moon. How come? Well, you guys need to look into it because I spent far too much time on this at one point in my life. I got so interested in the moon, I forgot what I was doing. When the moon, let's see that one of the giant moon in the sky, and we'll end up on that, okay? So,
Okay.
when the moon hit, or when Theia hit, they were both, the Earth and the moon were really close together. Right now, the moon's 384,400 kilometers away. Back then, it was about 20,000 kilometers away. So, Theia hits the Earth, they're right there together. The Earth is red hot, right? More than red hot, probably. It's probably white hot because it was molten. Also, the moon is red hot. Now, the moon is turning and the Earth's turning. They're both turning really quickly because it just smucked each other. It's just spinning. And that's probably what knocked the Earth like over on its side and gave it that tilt. So, they're both spinning really fast, but this is what happens. Because the Earth is so much bigger than the moon, let's see, the Earth is 12,756 kilometers in diameter, if you measure it around the waist, because it's thicker through at the waist than it is from the poles. And the moon's 3,771 or something like that. So it's a lot smaller. So the moon and the Earth get locked tidally. This is what I'm trying to tell you in my own fumbly way. They get locked tidally so that as the Earth turns and the moon turns, the moon is turning way faster than the Earth, but the rate at which they're turning makes the same side always face the Earth. So, if indeed the same side has always been facing, the same side of the moon has always been facing the Earth as it was at the beginning, then that's why one side looks different than the other. Because the side facing the Earth was getting all the heat, and the side on the other side was a lot colder. Because they're both turning at the same rate. So the far side of the moon stays cold, the near side of the moon gets hot, and that is why on the far side of the moon, the stuff that precipitates out first, that has the highest melting point, it settles down and gets thick, whereas on the near side of the moon, where it's hot, stuff isn't settling down and precipitating out. So everything that settles out on this side of the moon settles out way after the other side. It was thousands of degrees, or hundreds of degrees, I'm sorry, hotter on this side of the moon, on the near side of the moon than on the far side of the moon for a long time. So, also, there's the thing of radioactivity. This is where we end. There was a lot of radioactivity in the early universe. You know all the lead on Earth, right? A lot of lead. It's a common element. Do you know all that lead used to be uranium? Yeah. We have 2 main kinds of uranium, uranium-235 and 238. One decays, has a half-life. I told you about half-life last day, right? Rutherford invented it. Anyway, so it's got a half-life of 710 million years. That means in 710 million years, half of it's gone. So all the uranium on Earth, except for one type, which is called uranium-204, all the other uranium on Earth was formed by lead, and the lead is decayed. So if it's uranium-235, which has a long half-life of 446 million years, it's only had one half-life to go through since the Earth was created. But if you're uranium-235, which is the more potent type, of which they make nuclear bombs out of, then that kind has a half-life of 710 million years, so that's lots of half-lives. And you use those half-lives to date everything, because they tick off like an atomic clock, which is what they are. So they're perfect for this. So one side of the moon was hot, the other side was colder, and the side on this side, all that dark stuff that we showed you, is radioactive. It's got potassium and thorium and uranium, and it's decaying, and that heat is contributing to that problem. So what probably happened then is that the far side cooled and got thicker, the near side cooled much more slowly. It evolved a thinner crust, and the crust was made out of basalt, which is runnier and more metallic than the stuff on the other side. And remember those asteroids? Every time, okay, and show us the other side of the moon. I gotta make you do one last thing here. Okay? That side of the moon is the radioactive side. It's got a thing on it called CREEP, K-R-E-E-P. And CREEP stands for potassium, rare earth elements, and phosphorus. And the potassium is potassium-40. And it's along there with uranium and thorium, and they're radioactive as hell. So they've been radioactivity away up there for all that time, keeping that side hotter and thinner, because when the asteroids come down, they hit the thinner, hotter, more melty crust, and it runs all over the place. So it's been constantly erasing. Well, the bombardment ended around 3.1 billion years ago, mostly. But ever since then, that black stuff has been running and filling in the new craters. So all the biggest craters were early, the smaller ones were later on. A lot of the ones got filled in because this side of the moon stayed hotter longer than that side of the moon, which cooled off first. So that side of the moon is thicker and lighter. It's literally higher with a thicker crust made out of totally different stuff, and this side is different. Now, whether what I just told you turns out to be the right thesis or not, I don't know. That's one of many theories. But, honest to God, I'm quite sure within the next 20 years they'll have it all figured out. Okay? So, next week, man, we're on Earth, and we'll be looking at conditions of life on Earth. So, thank you very much for coming out. And I hope I didn't confuse you too